Hi, welcome back. We are at the end now of a very exciting session that started with, well, more or less the bare category theorem. There was two smaller results up front that sort of prepared the stage. Once we had bare, then we, with the help of a corollary to it, we obtained the principle of uniform boundedness, then the open mapping theorem. Once we had open mapping, again with the help of sort of a corollary to it, we then obtained the inverse mapping theorem. From the inverse mapping theorem, further corollaries, equivalent norms, and now we'll prepare the last part. So in the last video we defined the direct sum of normed linear spaces of NLS, and we had already one result up front about equivalence of norms, and now the last part has to do with the following new concept. So what we'll call the graph of a linear map. Now the graph of a function in real analysis is well known. If you have y equals f of x, and then the graph is simply all pairs x comma f of x. That's how you visualize a function in R2 after all, right? Here now this graph is very much the generalization of that green stuff to the normed linear spaces. So if you have a linear map up here, T, just linear, not necessarily bounded, equivalently not necessarily continuous, you define the graph as just a subset of the direct sum of x plus y. That's why we had to discuss it up front as well, all pairs x t of x, where x is in the domain of the linear map. All right. Now this is always not just a set, it's always a subspace. That's easy because of how the vector space structure was defined on the direct sum, just coordinate wise, but it's in general not going to be closed, right? And in fact, checking closedness of the graph will immediately tell us whether a given linear map is bounded, equivalently continuous, right? Notice, if that T up there is continuous, then the graph will be closed, right? But the other direction might not be true always, all right? So now, here's the theorem that goes the other direction. So this is the last big theorem in this very important section. Maybe I will move it a little bit further up now. So that's the closed graph theorem, right? So looking at the graph of a linear map can tell you whether the linear map is bounded or not. So let T be a linear map between two Banach spaces x and y. Then the simple statement is, if the graph of T is closed, then T is bounded. Okay, that's it. All right, so how to prove? Well, we're going to use the inverse mapping theorem for that. So by definition of the direct sum, let's look at this map pi1 x direct sum y mapping to x, and likewise pi2 x direct sum mapping to y. And what do? Well, they project. So if you have a pair x comma y in the direct sum, then what does pi1 do? Well, it projects on the first coordinate, and likewise pi2 is gonna project onto the second coordinate. All right. Now, first of all, these two maps, they are both they're linear. Okay, they're well defined and they're linear. That's clear, and they're also bounded. Hence, they are continuous. Right? Are both continuous. Right? Why is this? Well, maybe I will do one here. The other one is very much similar. So pi1, so this would be here, if I indicate this would be the x norm. Well, this is by definition equal to x in x space, and that is of course well, x plus I can just add capital Y here. I can just add a non-zero quantity to that, right? Y, non-negative quantity. Yeah, but this is precisely how the direct sum norms, now this is supposed to be a cross right here on the right, that is precisely how the direct sum norm was defined, right? So, and then here you have it. This one at most being equal to that one says that the operator norm of pi 1 cannot exceed 1. So it is bounded linear transformation and hence continuous. The same argument applies to the pi 2. You just have to change the subscripts from x, capital X to capital Y. All right, so they're both continuous. Very nice. Moreover, I will say clearly, and I will explain why this is clear. If you take pi 1 and you restrict it now to the graph of t, so remember the graph is a subspace of the direct sum of x direct sum y, then I claim this is a bijection between gamma t and x. Okay, so we already know it's linear and bounded, so the same holds then true for the restriction. So why it is a bijection? Well, first off, what does now pi 1 takes input from elements in the graph, and remember elements in the graph, they look like this: x comma t of x, and it sends it, well, it projects on the first coordinate, right? It's x. So now why bijection? Well, if that guy is equal to 0, so if you want to check for injectivity, well, then the equation immediately tells you that x has to be equal to 0. But since t is a linear map, well, then t of x is also to 0, right? So only the 0 vector in the direct sum is mapped to the 0 vector in x space. And the same thing happens yeah, that happens. That's the injectivity, right? Now the surjectivity, well, it's sort of the same argument. Because of this equation here, because any vector x in x, well, because of the projection is written like this, right? So it clearly corresponds to the input element x comma t of x, right? So it's clearly surjective, right? That's why put together this is a bijection. It is linear and it is bounded, and now. But remember, the inverse mapping theorem only works in Banach spaces, between Banach spaces. Yeah, but that's why you require the graph to be closed, right? But gamma of t is closed, so a Banach space. And now this restriction of pi 1 mapping gamma t to x is a bijective linear bounded map between two Banach spaces, right? And now you can apply the inverse mapping theorem, okay? So a Banach space, and so by the inverse mapping theorem, pi 1 inverse, let's write it as x going to gamma of t, with, well, what's the action? Now, yeah, that's easy to see. It maps x to the pair x comma t of x is continuous. All right, now we only need to realize since, so let's look at the composition now of pi 2 and that inverse pi 1 to the power minus 1. So that's gonna go from where? Pi 1 minus 1 takes input in x, it sends it to something in the graph, and then what's gonna happen with pi 2? Well, it's gonna project on the second entry, so that is an element in y, right? And how does it do this? Well, you have here the first action, and now the action of pi 2 on this thing, it's going to project on the second one. So it's going to spit out t of x. Yeah, but that's precisely what t does, right? So this composition is simply t, right? So now what you have realized here is that t is the composition of 2, that continuous maps, right? Pi2 we already said earlier is bounded linear, hence continuous, and we just found out that pi1 minus 1 through an application of the inverse mapping theorem is also continuous. So the composition is continuous, and that's precisely what you wanted to show. We have T was already linear by by assumption. Okay, and that's it. That's the end of the theorem. All right. Good. So this is short and sweet and quite powerful. We will apply it in a moment. So to deal with this application, I prepared here a short remark. Let me move this upstairs. Okay. So consider the below statements for convergent sequences X and a linear map between two normed linear spaces. So here are three statements. The first statement, sequence Xn converges to X, an element in capital X. Then second statement, the image sequence converges to some element Y in the target space Y. And then the third one, Y is actually the image of X under T. Right? So now, what do we know so far in this class? Well, continuity of T says what? Well, if I have A and a continuous continuous linear transformation, hence a bounded linear transformation, and then this implies B plus C, right? Because continuity simply says if you have xn going to x, then txn is going to t of x, and that is precisely here B plus C, right? This is B plus C. Okay, that's continuity. So that is old, right? Now, what does gamma t closed say? Gamma t closed says A plus B implies C, right? Is that true? Well, sure. Let's do it also in yellow. Maybe let's move it a little bit further down. It ripped out here some of the letters. Continuity of T says. So now, but here gamma T closed says what? A plus B yields equal to C. Why is this? Well, because if something is closed and you take a sequence in it, and after all the sequences in the graph, they look like this, right? So now the thing, this here would go to some, x by A in the first entry, and to some y in the second one, right? This is what you have by A plus B as n goes to infinity in the direct sum norm on the direct sum here of x direct sum y. And gamma t says closed. Well, gamma t closed says, well, y is equal to t of x, right? And that's precisely what you mean if you have a closed graph, right? So that we have this. And now what does the theorem say? Well, the closed graph theorem closed graph theorem says that, let's see, did I prepare anything else? Oh yeah, I have to move this a little bit further up. Save some space. Maybe like this. Maybe like that. So the closed graph theorem, what does it say? It says that one can assume A plus B and completeness of x comma y in trying to prove C to get continuity of t, right? Why is this true? Well, suppose you assume a plus b, so xn goes to x, txn goes to y. And now if you, this is pretty much that yellow stuff what's written up there. And now if you manage to show that y is equal to t of x, then you have shown that the graph is closed, because you have exactly managed to show what's written up there in this line, right? And once you have closed graph and you are in Banach spaces, hence you have the completeness there in place, then it immediately yields you the boundedness, aka the continuity of t, right? So this is what the closed graph theorem really does. Okay. Good. Here is one final application of the closed graph theorem. We will precisely use now this strategy that I just wrote down. So we will assume A and B. We will show, okay, we will be in Banach space scenario from the get-go. There's nothing to show there. And we will prove C, and then the closed graph theorem will kick in and show us that, well, continuity is satisfied. Okay, here's the result that I talk about. It's the Hellinger-Toeplitz theorem. So this is now the first time that we go back to Hilbert space world, because we need an inner product. So let T be a linear, just linear, not necessarily bounded. The statement of the theorem will tell us that under certain assumptions that thing is bounded, but it's not assumed that it is bounded up front. So a linear map from a Hilbert space with some inner product here to itself. Now suppose this map satisfies this property. So t of x comma y is the same as x comma t of y in inner product. So the action of t, whether it is on x or on y, is going to spit out the same result. This condition will play a very distinguished role in the last chapter of this course, and once we are there I will make a comment and go back to this. But for now let's just accept the yellow box. Then the statement is, once this happens, then t has to be continuous. Okay, that's the statement. So how to prove? Well, I already said what we're going to do. So we're going to take the convergence sequence xn that goes to x and txn that goes to y. We are certainly in a complete space because we're working here with Hilbert spaces. And now what we're going to show is that y is equal to t of x. And that will show that the graph of t is closed, and then the closed graph theorem will kick in and give us the statement or the claim. All right. So let's do this. Then for all z in the Hilbert space, by continuity of the inner product, which is a consequence of Cauchy-Schwarz inequality, what do we have? Z t of x is, so now I'm going to use the box first here. I'm going to shuffle the t from the second vector to the first vector, and that's going to leave the inner product invariant. So I have this. And now I'm going to use that, well, x is the limit of xn. All right, now I use the continuity of the inner product, and I can move the limit outside. tz xn. And now you shuffle back. The limit outside just stays as is. So here now I use it for the second time. And I have z txn, and then I go inside. So let's present all the steps. Txn, and this is up there y, right? C of y, all right? So you have this is equal to that for all vectors z, all right? Choosing z as tx minus y, which is certainly a vector in the Hilbert space, we obtain, well, what does the green stuff tell you? Well, if you bring this right-hand side here to the left and use the properties of the inner product, then you have z in the first vector, inner product tx minus y is equal to 0, right? But now I choose z as tx minus y, and this explains why I do this. So I have this, yeah, but this is precisely telling me that the norm of tx minus y is equal to 0, and remember the definiteness of a norm, that's precisely going to happen when tx is equal to y. Huh? So we're done. Hence, gamma of t, the graph, is closed. And so, by the closed graph theorem, t is continuous. So altogether, a bounded linear operator on the Hilbert space. Okay, and that's it. All right, so that's beautiful. Why does one care for this Hellinger-Toeplitz theorem? Well, this is one of the first instances where you can actually build a bridge to applications in mathematical physics, for instance in quantum mechanics. So if you've ever taken a class like this, you can listen. If not, you can fast forward in the video. So in quantum mechanics, there are certain observables that are represented by operators. For instance, the energy of, say an electron in some trap, right? So that operator is the Hamiltonian. It physically represents the energy. Now, and the Hamiltonian typically satisfies this constraint here. That's what you want from it. However, the Hamiltonian typically is sort of an operator that involves derivatives, right? So more precisely, it typically involves these second order derivatives, right? So now the thing is this: so the derivative operator, unlike the integral operator, is unbounded, and you can easily see this. So if this is your operator, say d, if you look at, say, sine of x, that is a, well, continue to as many times differentiable as you like, but certainly twice on, say, 0, 1. And now if you start differentiating the sine function once, then already in the first application, that n here comes out, right? So that's never going to be bounded. When n goes to infinity, that's going to escape off, right? So that's an unbounded operator. Still, you want it to satisfy this yellow box. Yeah, but this means then in turn that the operator cannot be defined on the entire Hilbert space that you're working on, right? Right, because I apply Hellinger-Toeplitz backwards, right? I negate the statement. I have an unbounded operator, so this is not true. That wants to satisfy the yellow box. In turn, this means the operator cannot be defined on the whole Hilbert space. That's a physical application. All right. So that in other words, the study of unbounded operators is quite different than from what we're doing here in this introductory functional analysis module. It's something that you usually were to do in a sort of follow-up module. Okay, good. Anyway, so now this result here, Hellinger-Toeplitz, that closes up the section on Baire category theorem and its applications. Now we're going to start the last section in chapter 3. Chapter 3 certainly is the longest chapter in this module. The basic theory about Banach spaces. There's lots to be covered, and we have covered already quite a lot of material here, much more than in the Hilbert space world. So now the last point here is a new convergence type. That last section, it will build up to the first section in chapter 4, which will again deal with convergence types, but slightly different one. But nevertheless, we should take this as a preparation. All right. So to motivate the new convergence type that we will learn about, let's do one example here. So look at the Hilbert space, square summable sequences with this inner product, and look at our favorite, now I can use the word basis because that is a separable Hilbert space. It has a linearly independent spanning set given by these ENKs, where, just to remind ourselves, the ENKs are most of the time equal to 0, and only once they give out something non-trivial, right? Where this and these guys obey, obviously, En minus Em in 2 norm is equal to square root 2, which is positive for all n different from m, right? That's a simple check. So if you subtract two of these guys, one index n, the other one m, and m, if n is equal to m, then of course you get 0 because you subtract the same thing from one another. But if you don't, as easy check is you get a sequence that has two non-zero entries. One is 1, the other one -1. But if you look at that 2 norm there, they're going to sum up to 1 plus 1 is 2, and then you have to take a square root. So that's why square root of 2, and that's clearly positive, right? So this means in particular, in turn, the sequence of the ENs is not a Cauchy sequence, and hence does not converge, hence does not converge in H. Okay, I will stop here. Now, one more line. We'll realize that actually there's a different convergence type, a different notion of convergence that will make these guys convergent. And this is what the header says here. This is a weak notion of convergence, right? So although these ENs, they do not converge in the ordinary 2 norm here on the Hilbert space, there is a different type of convergence out there. That's the weak convergence. Which is weaker than the norm convergence. That's why the word weak. And in that notion, it will converge. All right. So I will define this notion early on. Then we will gather basic properties of this convergence type, some tests, how you can check for it, and then gradually we will build up more theory in this section. I will see you soon.